Hello everyone, welcome back to our generator protection playlist. In this video we will discuss the reverse power protection function 32. This protection plays a key role in turbine-driven generators, especially steam turbines, to prevent the mechanical damage or overheating during the shutdowns. We will explore how the reverse power relay detects motoring conditions, why it's critical to trip the generator breakers, and how the settings are chosen based on the turbine type and operating characteristics. Let us get started with the concept and the operation of the reverse power protection. The reverse power protection, also known as a function 32, this protection is mainly associated with the turbine-driven generators, particularly steam turbines. So its purpose is to prevent the turbine from being driven by the generator as a motor in case of the steam supply is interrupted, while the generator remains connected to the system. So when this happens, the turbine can overheat because there is no steam for cooling or control. The reverse power relay detects this motoring conditions and trips the generator circuit breakers, ensuring that the steam valves are fully closed and the machine is safely shut down. In the large steam units, the relay must be very sensitive and able to operate accurately even at low power factors. This setting is usually only a few milliamps with a trip time of about 3 seconds to ensure a protection against damage during normal or emergency shutdown. So for practical measurement follows approximately 3% of for closing the main valve and 3 up to 7% of the emergency stop, and therefore the setting of a few milliamp is usually chosen, and the trip time setting should be approximately 3 seconds. Now we will talk about the motoring protection. So the generator acts as a motor when the mechanical input power to its shaft is lost while connected to the power system. Assuming that the generator field is unaffected, the generator becomes a synchronous motor driving the prime mover at a synchronous speed. But if the field excitation is also lost, the generator may lose the synchronism and become an induction motor. Assuming that excitation is maintained, the generator can operate as a synchronous motor as we explained, so the motoring is damaging to the prime mover, not the generator. Motoring can result from operator error, a failure of generator breakers to open during shutdowns, or because of mechanical failures. So electrical motoring protection in the form of reverse power relay designated devices called 32 protection relays, and this relay detects the power flow into the generator terminal from the power system. So the reverse power relay traps the generator breaker, the field breaker, and the prime mover. Now we will talk about the electrical protection of the motoring effect. So when the prime mover, the energy input to the generator stops, the generator begins drawing power from the system to cover its losses. A condition detected by the reverse power relay, the required relay sensitivity depends on the prime mover. Steam turbine under full vacuum typically need from 0.5 up to 3% of the rated kilowatt, while non-condensing units may need higher settings. Modern microprocessor relays usually include two reverse power elements, one for the motoring protection and another for sequential trip logic, and allow fine per unit adjustment such as plus or minus 3 per unit. So this relays measure powers using the formula B equal I multiplied by V multiplied by cosine theta, and to provide a precise and reliable detection even at low power factors. And you can see from the screen here the PQ diagram to check the power setting. You can see from here. So here is the SEL detection relay parameter setting, and as you can see here is the power level threshold, which is equal to minus 0.002, and the level 1 power time delay equal to 1 second. Also we have a level 2 with the same threshold but with a delay time equal to 60 seconds. So you can see from here the 0.002 per unit, which representing the reactive power or the reverse power setting. So speaking about the consequences of the motoring on the prime movers, we have different type of prime movers which can face unique risks when motoring occurs. For example, for the steam turbines, the lack of steam flow means no cooling, causing a heat buildup, especially at low pressure plates, which can lead to thermal stress and deformation. On the other hand, for hydro turbines, which can experience cavitation while motoring, as a runner acts as like a pump and damaging the plates over time. For the engine-driven generators, the motoring after a mechanical trip can be dangerous because unburned fuel or overheating parts may lead to a fire or explosion. And in a gas turbine or a gear-coupled system, the reverse torque during motoring stresses the gears in the wrong directions and leading to wear or failure. So to prevent this problem, the reverse or low forward power protection is used to trap the breaker when the power flow indicates unsafe motoring condition. When it comes to the mechanical motoring protection, so especially for steam turbines, we focus on detecting the unwanted motoring conditions through several signals. So the exhaust hood temperature is quite sensitive since motoring heat builds up, but it's mainly used for alarms, not tripping. A more reliable indication comes from trip and governing oil pressures, which show whether the steam valve are actually closed. Also, limit switches can be used, but they tend to misoperate on the large machines. Another effective approach is the differential pressure detection, measuring the pressure drop across the turbine to confirm whether steam flow still exists. However, a valve leakage or backflow can still cause a false motoring signals or even overspeed if not managed properly. So that's why a mechanical system are often supervised by a reverse power relay, ensuring that steam flow has truly stopped before tripping. For hydro units, the flow indicators and the reverse power protection are used, but for synchronous condensers, motoring is normal and controlled, so reverse power protection is not applied. So now we will start with the overview about the reverse power detection. As you can see, when the unit loses its mechanical input, for example, due to a turbine shutdown, it can begin drawing a power from the grid to keep spinning. So this condition is detected by the reverse power relay connected at the generator terminals, which monitors the power flow direction. So if power flows into the generator instead of out, there is indication of motoring. And the sensitivity of this detection depends on the type of the prime mover, as we explained. For condensing steam turbines operating under vacuum, even a small reverse power level, about 0.5 to 3% of the rated power, indicates motoring. And if the condenser vacuum is lost, a higher setting will be needed. So it's always best to refer to the manufacturer data for the exact motoring power limits and safe duration. So when it comes to a relay selection, we have electromechanical, electronic, and modern microprocessor types. The new digital relay provides a higher precision, easier calibration, and multiple setting options, often with two independent reverse power stage for motoring and trip logic. So finally, this relay measures the relay power using the formula P equal I multiplied by voltage multiplied by cosine theta, where the direction of power flow determines whether the generator is producing or motoring. Now we will talk about the sequential trip logic. So the sequential trip logic ensures a safe generator shutdown by reducing the prime mover input before disconnecting from the grid. The reverse power relay serves to two key rules here. So detecting the motoring and supervising that the reverse power exists before the generator breaker opens. So this prevents overspeed, especially in the turbines with steam valve leakage. And this sequence is very simple, as you can see from here, the sequential trip logic. So cut off the prime mover and wait to 2 or up to 3 seconds for reverse power to appear, and then trip the generator breaker. So finally trip the field breaker to avoid loss of feed. So this logic is used for steam, gas, and hydro units, but not for the fast trips like generators or generator step up fault. So typically a 3-second delay is applied to allow a safe energy dissipation and prevent a false tripping during transient events. And here in this slide, we look at testing formulas used for reverse power protection under a balanced three-phase condition. So we start with the assumption that the applied voltage equals the nominal value, and we calculate the per unit real power based on the applied current and the phase angle between the voltage and the current. So by adjusting this angle, which is angle theta in our case, we can simulate a low power factor conditions, which are especially useful for verifying the sequential tripping behavior. But remember, when working with the phase-to-phase connections, you have to adapt the phase angle. So the phase angle must be corrected by subtracting 30 degrees to reflect the actual vector relation. So you can see here BU stands for the per unit real power, V is the applied voltage, here is the nominal voltage setting, here is the applied current and the nominal current setting, and theta is the voltage to current phase angle in case of phase to ground, and voltage to current phase angle minus 30 degrees in case of phase to phase. Now we will talk about testing the reverse power protection. Starting with the setting from left hand of the screen, you can see the reverse power picks up at minus 2.9%. The delay time without emergency tripping equal to 10 seconds, and with emergency tripping equal to 1 second. So we can calculate the secondary power levels. As you can see, the S and secondary value equal to root mean square of 3 multiplied by V nominal and multiplied by I nominal. And you can calculate this V nominal of the generator. For example, in our case, we have a VT ratio equal to 10 kV divided by 100 voltage in secondary. So we can calculate the nominal voltage of the generator in secondary and in phase to phase by using the formula 10.5 kV, which is the generator primary divided by the VT ratio, which equal to 105 volt. So the V nominal in phase to earth will be 105 divided by root mean square of 3, which equal to 60.62. And also using the formula, which is the power in our case equal to 2.5 megavolt ampere, and voltage of the generator equal to 10.5 kilovolt. So we can calculate the primary current of the generator, which is 2.5 megavolt ampere divided by root mean square of 3 multiplied by 10.5 kV, which equal to 137.4 ampere. So the current in secondary will be 137.4 divided by 150, which is the CT ratio, so it will be equal to 0.916 ampere, so 916 milliamp in our case, which is this value we are using to calculate the secondary power values in secondary values, which equal to 166 volt ampere. Then you can use the reverse power setting, which is minus 0.029 per unit, to calculate the actual volt ampere values, and from this ratio we can get the current in this setting, which is minus 4.8 divided by root mean square of 3 multiplied by the rated secondary generator voltage, which is 105 volt. So the current will be 26.57 milliamp. So in this test we are verifying the reverse power protection 32, but for a nominal secondary voltage, the pickup value of minus 2.9% corresponds to a secondary current of about 26.57 milliamp. Also, we have to define the local hardware configuration. As you can see, we will use the 3 voltage output mapped as a phase to neutral voltages, and 6 current outputs with current system A assigned to S1 and current system B assigned to S2. So finally, also the start signal we need to be mapped to a binary input of the CMC to ensure the relay correctly detects the reverse power conditions during the testing. Okay, speaking about the first test, which is the pickup value of the reverse power protection, as we explained, we can use the ramping module. So the ramp 1, we will need the start condition as a trigger condition, changing from 0 to 1, and the nominal value of the current to be 26.58 milliamp, and here is the allowed tolerance based on the relay technical specification. On the ramp 2, we will need the trigger condition to be start from 1 to 0, and here is the expected drop off value of the current, and with the tolerance plus or minus allowed tolerance. So the signal 1 we are using here is the magnitude of the test current on side 1, and signal 2 will be the magnitude of the test current on side 2, and we will ramp from 85% up to 120% of the pickup value, and back also in ramp 3 to get the drop off value. So we are ramping up the current in ramp 2 and ramping down the current in ramp 3. Also in the analog output view, as you can see from here, a phase shift also about 180 degree between the current on side 1 and current on side 2, and this current also to be set in analog output view of the detail view. And also in the measurement view, you can define the assessment of the pickup value and the drop off value of the current, as you can see. And so ramp 2 will be used for assessment of the pickup value, and ramp 3 will be used for assessment of the drop off value. And in the calculated assessment, you can get the drop off over the pickup value, which is the reset ratio in this case. Now we will talk about the second test, which is testing the trip time without emergency trip. So we will use the sequential module here to test the trip time of the reverse power protection without emergency tripping. So the state number 1, we will simulate the nominal power. So we will use the nominal voltage and the rated current, which is 916 milliamp for 3 seconds, to ensure the reset of all possibly bending trips commands prior to the actual test. And also state 2, as you can see from here, state 2, you can see the current angle here is 180 degree to simulate a reverse power status. And also in the detail view, you can change the set mode to be powers, and this way it's possible to directly define the test quantity as a secondary power value. For example, 1.5 from the reverse power setting in secondary values, which we can use it in the state number 2, as you can see, with a double time expected with no emergency trip. So we are expecting 10 seconds, so we can make it for 20 seconds, and state number 3 would be for the post fault. And also you can see here the ramp assessment view for the nominal time, which is 10 seconds, to be measured here and to be assessed, as you can see. But you have to take into consideration also the long pickup time of about 360 milliseconds must be considered in the tolerance band to assess the trip actual time. Now test number 3, how to test the seal in time. We will use the same local hardware configuration. Also we will use the test sequential module to test the seal in time of the reverse power protection. So for example, we will use the state number 1 with the nominal power for 3 seconds, as you can see, without any binary trigger needed. But on the state number 2, we will simulate the reverse power by equal to 1.5 multiplied by of the reverse power setting, as you can see, and the phase shift also to be 180 degree to simulate the reverse power, and the time limit in state 2 must be shorter than the seal-in time configured in the protection, which is 1 second. So here is 450 milliseconds is less than 1 second, which is okay. And in the state number 3, we will simulate again the normal power with normal voltage and rated current for 3 seconds again, and the time limit in state number 3 must be longer than the seal-in time configured in the protection, must be longer than 1 second, so 3 seconds is more than enough. And in the measurement value, in the measurement view for the time assessment, here we will use the start contact from 0 to 1 as a start condition, and the stop to be from 1 to 0, and we are expecting 1 second as a seal-in time, as you can see from this diagram. So the seal-in time will be started by the starting condition, as you can see from here, up to the start to be off conditions, changing from 1 to 0. And here is the reverse power starting on the state number 2, and it takes approximately 360 milliseconds to pick up the reverse power protection, as you can see. Then we can measure the 1 second as a seal-in time. Here is test number 4. We need to test the trip time with emergency tripping. Emergency tripping, so we need to simulate the stop valve. And the stop valve signal must be wired to the corresponding binary input of the protection relay via the binary output number 2, as you can see from the detailed view of the binary output view. So, because as we explained, the reverse power protection 32 can be seen as a pure turbine protection. So it prevents that the turbine is driven by the generator working as a motor if the steam supply is interrupted while the generator is still connected to the network. So hence the turbine tends to be overheated due to the missing steam. The reverse power protection must trip the circuit breaker considering that the condition that the valve is still closed. So we will use also the state sequencer as we explained. So state number 1 for the nominal power up to 3 seconds. State number 2 for the reverse power 1.5 multiplied by the reverse power setting for time more than the expected trip time. So the expected trip time in the setting is 1 second, so we can put it 3 seconds. And state number 3 would be the post fault. So also in the analog output view, you can change the set mode to be a power. So this way it's possible to directly define the test quantity as a secondary power value, which should be equal to 1.5 multiplied by the reverse in secondary values as explained in state number 2. And also here is the stop valve in the detail view. The most important here is to simulate the stop valve, and also the binary output 2 of the CMC is wired to the corresponding binary input of the protection relay. But if the binary output 2 of the CMC is not used for the simulation of the stop valve signal, this signal must be simulated externally prior to the test start, and then you can define the time assessment in the ramp assessment view to detect the trip time with emergency tripping. And here is the end of our video. Thank you, and see you in the next video.